Good evening, everyone. My name is Kim Strong, and I'm the chair of the Department of Physics here at the University of Toronto. It's my very great pleasure to welcome you to the 2024 J. Tuzo Wilson Public Lecture. I'd like to start my remarks with the official U of T statement of acknowledgement of traditional land. I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still a home to many Indigenous people from across Turtle Island, and we're very grateful to have the opportunity to work on this land and to attend talks like this one. This statement seems particularly relevant given that the J. Tuzo Wilson Public Lecture has its focus on the Earth. So as many of you probably know, this lecture is an annual event put on by the Department of Physics at U of T. Each year, we commemorate the life and the work of John Tuzo Wilson, who was one of the key discoverers of plate tectonics. Tuzo Wilson was fascinated about the study of the Earth and convinced that beneath all the chaotic wealth of detail in a geological map lies an elegant, orderly simplicity. That's a quote. He himself had the wonderful capacity to assimilate and retain the detail while arriving intuitively at simple and elegant models. He was born in 1908 and died in April of 1993 at the age of 85. So he died just about 3 years before I arrived at U of T, so I did not have the pleasure of meeting him in person. During his professional career, he began to use his middle name, in case you're wondering about the Tuzo. That was to avoid confusion with another J.T. Wilson. So Tuzo Wilson's association with the Department of Physics goes way back to his undergraduate days. He arrived in the mid-1920s, and in 1930, he was the first Canadian student to graduate in the field of physics and geology. After that, he headed to Cambridge, and then to Princeton, which is where he earned his PhD. Then he went to the Geological Survey of Canada and the Royal Canadian Engineers, where he worked during World War II. In 1946, he received a call from Professor Burton, who was the head of the physics department at U of T at the time. Professor Burton asked if he would accept the position of Professor of Geophysics in the Department of Physics. It was a little easier than it is today. We're in the middle of multiple job searches at the moment in the department. So he accepted, moved to Toronto in June 1946, and became the only professor of geophysics in Canada at that time. Just after World War II, very few of the world's universities had any significant specialization in geophysics, and there's really none in Canada except at Toronto. Over the following 2 decades, working out of an old house at 49 St. George Street, Tuzo Wilson led and inspired a group of geophysicists here that was unique in Canada and quite notable globally. Something like 40 PhD students graduated between 1949 and 1965, and another 39 between 1966 and 1980. Apparently, those who worked on the winter weekends had to shovel coal into the furnace to maintain reasonable temperatures. Building still had problems. No, it's too hot in our building. Wilson's life ambition was to understand global geology. And from 1961 to 67, he really became a major player in creating the field of plate tectonics, which was the new global view of how our Earth works. He remained in his position for almost 30 years, during which time he made a series of famous contributions to the ideas of ocean floor spreading and continental drift, and he was an acknowledged leader in the study of the Earth. Tuzo Wilson's achievements were recognized with a very large number of awards and honors, but his influence extended well beyond geophysics. He was appointed as the first principal of Arundel College, which is now University of Toronto at Mississauga, or UTM. And he was apparently infamous for entertaining some 10,000 guests in his home over a period of 7 years. He also served as president of the Royal Society of Canada, Director General of the Ontario Science Centre, and Chancellor of York University. We commemorate Tuzo Wilson and his many contributions with his annual lecture and with the J. Tuzo Wilson Professorship in Geophysics. This professorship is awarded to a geophysicist at U of T for a 5-year term. The holder presents an inaugural lecture during the first year of their appointment and organizes a public lecture by a distinguished geophysicist for the subsequent 4 years. So I'm very pleased to introduce our current J. Tuzo Wilson professor, Jinya Liu, who is cross-appointed to the Department of Physics and the Department of Earth Sciences. Professor Liu is a computational seismologist who uses seismic data to probe the structure of the Earth's interior. And in this, she's a very fitting successor to J. Tuzo Wilson. I'd also just like to note that this is the last year of Chinya's 5-year appointment. And so I'd like to take this opportunity to thank her for all the excellent Tuzo Wilson lectures that she has organized over the last 5 years. I'm sure tonight's lecture will be another fascinating journey into the field of geophysics. So I'll now pass the microphone over to Chinya to introduce our speaker.
Good evening, everyone. Welcome back to the 2024 J. Tuzo Wilson lecture. Like Kim was saying earlier, I was honored to be the J. Tuzo Wilson chair for the past 5 years, organizing these really exciting lectures. And it's very exciting also here to see old friends and colleagues and also some new faces back in back there. So today we're very honored to have Professor Richard Allen here to give the Tuzo Wilson lecture. So Professor Allen received his bachelor degree from University of Cambridge in 1994, followed by a master's degree in Department of Geology and Geophysical Sciences at the University of Durham before heading for a PhD at Princeton. You can see the overlap really, or the sort of a similar path as Tuzo actually took from Cambridge to Princeton. That's great coincidence there. And after spending a year as a postdoc fellow at Caltech, where I actually overlapped with him for a year, he first became assistant professor at University of Wisconsin-Madison, and then at UC Berkeley in 2005. He has since become the director of the Berkeley Seismology Lab and the class of 1954 endowed professor of Department of Earth and Planetary Science at UC Berkeley. In addition to some of these early notable seismic imaging work for tectonic regions like Iceland, Cascadia, and Alaska, he's also a renowned expert in earthquake alert systems. In particular, he has led the development of methodologies to detect earthquakes and issue warnings prior to shakings using seismic and GPS sensor networks, as well as recently smartphone networks. His group developed the earthquake early warning algorithms that generate alerts in the US, the so-called Shake Alert system, Israel, South Korea, and most recently coming to Canada, which I think Professor Allen's going to touch upon. So Shake Alert was an awesome inspiration for Google's global Android earthquake alert system, which I was trying to use today earlier, but apparently wasn't available for our region yet. But this was named one of the greatest innovation in 2020 by Popular Science. So working at the intersection of science, technology, and public policy, Professor Allen interacts extensively with both state and federal government agencies, giving out testimonies and briefings for legislatures and senior government officials, including, I was reading, California Governor Gavin Newsom and the White House, to name a few. He is also a senior staff scientist at the earthquake team at Google. So today we're very excited that Professor Allen's going to tell us a bit more about the earthquake warning system. So without further ado, Professor Richard Allen.
I'll explain what I mean by that in a few moments, but that's what this is. So thanks to my colleagues at Natural Resources Canada, I have a few slides just to talk about earthquake early warning as it's coming to the east coast of Canada. And just to sort of set that, to me, that's a real successful outcome for earthquake early warning. Earthquake early warning, of course, is about protecting people in an earthquake. But I would also like to see that as a product for people also drive science. We have earthquake early warning because we have regional networks and we've learned about the earthquake process. And so we've developed methodologies to reduce the hazard. And so I think it's only appropriate that now that we have the product, we can start to build bigger seismic networks, which will feed into that cycle of delivering better earthquake reduction strategies. And this example of the east coast of Canada is a great example of that. Okay, so let's jump in and let's start at the beginning. So what is earthquake early warning, first of all? So this is an animation. Obviously, it's a cartoon, but it's running in real time. This is a magnitude 8 earthquake on the San Andreas Fault. So it's starting up here at the northern end of the San Andreas Fault, and this brown swath is the rupture that's going to come all the way down past the Bay Area to make it a magnitude 8. Now, these circles that are emanating, they represent the P waves and the S waves that radiate from the fault as the earthquake is underway. So the P wave travels the fastest, and so this yellow circle is the P wave. So if you were in San Francisco or in Berkeley, while this earthquake was going on, we would feel that thud of a P wave right now, okay, for a magnitude 8 earthquake. But we wouldn't know it was a magnitude 8 earthquake, right? We would feel a good shake, but we wouldn't have a sense of the true size of the earthquake. And the really strong shaking, the kind of shaking that would do damage, isn't going to start until the S wave. So the red circles represent the S wave that are emanating from this fault. And you see that the S wave is only going to arrive in San Francisco and Berkeley right around now. So now we really would be feeling strong shaking, okay? And if you lived in California, you would know to be down on the floor between these seats so that things don't fall on top of you. But still, this is not the most damaging phase of shaking. The most damaging phase of shaking is actually the S waves that come from the rupture itself when the rupture travels closest to where we are. So again, if we're in San Francisco or Berkeley, it's not until this rupture here has worked its way all the way down here and the S waves travel across the bay that you get the really strong shaking, the shaking that's going to do damage to buildings. And so this illustrates the concept of earthquake early warning, right? So earthquake early warning is not about predicting when an earthquake's going to happen. Earthquake early warning is about rapidly detecting when an earthquake is underway and then sending out a warning to people ahead of the ground shaking so that people can protect themselves. I tell people, so right about now is when the strongest phase of shaking is happening in the Bay Area, basically, because the rupture has come down. Again, this is running in real time. This is the equivalent of real time. So what I tell people is that we expect seconds to tens of seconds of warning, because that's a more typical amount of warning time. So it's seconds to tens of seconds, but as shown by this, it could be up to a minute of warning time before the really strong shaking. And so what we want to do is we want to take advantage of that warning time and use that to reduce the impact of earthquakes. Okay, so why do we need earthquake early warning? Okay, this is this is a video from a magnitude 7 earthquake in Mexico City. That siren you can hear in the background is the early warning system in Mexico City. So they have an early warning system, they get about a minute's worth of warning, and they sound the siren across the city so people know to get out of hazardous buildings. So that's why these people are out of this building, because they got the early warning, they got out of the building, and we can see why they needed to be out of the building. So this is obviously an extreme case, but this shows the value of early warning. It shows the fact that the early warning, the building collapse doesn't just happen immediately. It takes time. It takes time for the P waves and the S waves to get to a particular area, and then it takes time until buildings actually collapse. So there is time there that we can use to reduce the impacts of the earthquakes, as shown here. Now, that's an extreme end member case, perhaps a more realistic case or a more common case of how earthquake early warning can be used. It's about reducing falling hazards. When we look at the two most recent damaging earthquakes in California, it's Loma Prieta and Northridge. And so this is a photo from the Loma Prieta earthquake in the Bay Area. More than 50% of the injuries were due to people falling over. Okay, And then in Northridge, more than 50% of the injuries were due to things falling on people, right? Things like ceiling tiles, lighting fixtures. We're very fortunate that at least on the West Coast, we have buildings that are expected to withstand shaking for the most part. But the lighting fixtures, the ceiling tiles, bookcases are expected to come down. And if one of them hits you on the head, you're in serious trouble. So the point is that more than 50% of the injuries in these earthquakes were linked to people falling over or things falling onto people. So the argument for early warning is very straightforward. If everybody receives a few seconds of warning, if everybody drops, takes cover and holds on, then we just reduced the number of injuries by 50% in an earthquake. Okay. Now, I had to go and advocate for early warning at various government agencies like you just heard. And so that isn't enough, unfortunately. We need the next line, which is that the cost of injuries in the Northridge earthquake is estimated to have been about $2 to $3 billion. Okay, so all of a sudden, the value of early warning becomes a very easy argument to make. And that's why we have an earthquake early warning system today. I have these just to remind people that even in the places where we have the best building standards when it comes to earthquakes, there's still serious risks. This is the equivalent of a big box store, like a Home Depot or Walmart. In this one comes from New Zealand, as you can see. This is an example of, this is the airport in Chile, very high standards, but again, ceiling tiles coming down, things like that, a little more serious in this case. And then this is a concert hall in Japan. And so this is just to give you a sense of these are the kinds of hazards that we have to worry about in earthquake country. This is what we want to use these seconds to tens of seconds for to reduce the overall impacts of earthquakes. Okay. Okay, the other use, I don't want to just pass this by, but I will do after this slide, is sort of automated control. If you have earthquake early warning, you can use it to stop trains. The BART trains in San Francisco, for example, stop automatically due to earthquake early warning. Same for the LA Metro. You can use it to isolate hazardous machinery and chemicals, things like that. Data security is a big issue, and then situation awareness. So there are automated actions as well. It's not just about personal safety. There's these automated actions as well. Okay, so that's what earthquake early warning is. That's why we have earthquake early warning. So when I talk to people about early warning, there are several stories behind early warning. I've alluded to some of them already. But first of all, there's the public story, right? So to make earthquake early warning happen, there's the public story. There's what we had to do in the public domain. And it's a really nice illustration of how scientists have clubbed together and kind of made the case to expand applications to reduce hazards, but also to further the science. So the public story goes all the way back to April 2011. That was the Tohoku-oki earthquake in Japan, the magnitude 9 earthquake in Japan with a huge tsunami that you probably remember. And we organized a meeting within a month of that to bring legislators together, scientists, obviously, and the private sector to talk about earthquake early warning and really try and spur the development of the earthquake early warning system. And an outcome of that meeting was the Shake Alert system that we have today. That Shake Alert is the name of the US earthquake early warning system on the West Coast, so California, Oregon, and Washington. A few years later, we managed to persuade people at the White House and the White House Office of Science and Technology Policy to have a summit about earthquake early warning. Again, we sort of advocated for this, and that summit was actually what led to MyShake. MyShake is the app that we use to deliver early warning. I'm going to tell you about MyShake in a few moments. And then you can see how long it took from this meeting in 2011 to public warnings started in California in 2019. And it was actually those public warnings, so this was public warnings from the Shake Alert system delivered to the MyShake app that really spurred Google to get interested. And then a year later, Android got involved in earthquake early warning. So there's a real sort of snowballing effect of all this. So this was the public story. So if you talk to people in California, they're sort of familiar with some of these elements. Okay, so that's the public story. But there's another story. The other story is this one of data, as I mentioned a few moments ago. So when we started developing early warning, this is what the seismic network looked like. So the seismic network was put out for research purposes. It was a real struggle to get it funded, just to keep the network running so that we had information about earthquakes. But once we had earthquake early warning as a product, that obviously provided the impetus to expand the network. And so we started out on the West Coast with about 600 seismic stations. And we've been growing this network for the purpose of earthquake early warning over the course of the years. Right now, we're at just over 1,500 stations on our way to almost 1,700 stations. And so the point here is that this is the other story for the science community. This network is built for early warning, but it's also providing a network that we can use to do our science, to understand earthquake processes. A whole variety of studies are done using this network that we have. So that's the other story. And as I mentioned, it's just been fantastic to see that now extend into Canada. So this is a map of the network that's been deployed over the last few years by Natural Resources Canada to extend the early warning system on the west coast of Canada. And then this is the network that has been put in place to extend early warning to the east coast of Canada. And so the plan is to roll out on the west coast in April of this year, and then to roll out on the east coast later this year. So again, another 150 stations or so that have been put out in order for earthquake early warning, but can be used for research as well of course, in the coming years. And then there's a third story. The third story is the smartphone story. And the third story is, it's again about networks. It's about seismic sensors. It's about collecting data to understand the processes that are going on. But the smartphone story has two elements to it. It's about delivering alerts to people. If you're going to get alerts to people when they have a few seconds, what is the best way to get it to people? The answer is on their phones, getting it to their phones. But we can also use smartphones to detect earthquakes. And so the third element of this is the smartphone piece. MyShake is the app that we developed at UC Berkeley. We developed it originally to detect earthquakes, but then it became the way that we were delivering earthquakes. These points are all the places around the world where people have downloaded the MyShake app. 3 million downloads, over 3 million downloads at this particular point. And so the success of that, as I've already mentioned, sort of fed into the effort at Android, where there are now 2 billion devices detecting earthquakes around the world. So there's been this sort of expansion of our network, our observational capabilities as a result of the product that we're producing. Okay. So here's what I want to talk about today, having given you that little sort of overview. So with these seismic networks, they're rapidly expanding, which is great. And so the question is whether how we're doing. So does earthquake early warning work? We've been doing this for a while, since 2019 in California now, so we should be able to make a clear case that earthquake early warning is working. So that's the first thing I want to talk about. I then want to kind of address this question of smartphone seismology. What is smartphone seismology? What are the possibilities with smartphone seismology? And that will feed into the last section that hopefully I'll get to, which is, now that we have all of these seismic networks, what else can we do with this data? Okay, so that's our marching orders for the rest of the evening. So let's start with how good is earthquake early warning. Okay, so first of all, let's step back. Let me just kind of orient you. How exactly does earthquake early warning work? What are the elements that go into the earthquake early warning system? Obviously, we start out with the sensors. So the earthquake early warning system in the West Coast, the system that's expanding up the coast into Canada in a couple of months, it starts out with the traditional network of seismic sensors. So a regional seismic network that we use to collect the data. That, of course, feeds into algorithms that are detecting earthquakes in real time. Obviously, there aren't any people involved in this. And there are several algorithms that we use. The EPIC algorithm is the one we've developed at Berkeley. It's a point source algorithm. It's the fastest approach to earthquake early warning. It's actually been the algorithm that has generated the first alert for all alerts in California, Oregon, and Washington so far. Finder algorithm is now, once the earthquake starts to get bigger and bigger and bigger and become a finite source, the Finder algorithm recognizes the finite extent of the source so that we can do a better job of predicting the really strong ground shaking over a large region. And then GFAST is a geodetic-based algorithm, so we're also using the geodetic network to detect the earthquakes for really big earthquakes. So these algorithms all process this data automatically, and they generate a warning. And so that portion of the system, that is Shake Alert. That's what we call Shake Alert. That's the system. It's led by the USGS, but in partnership, obviously, with the universities that run the seismic networks up and down the West Coast. And then, of course, we have to disseminate the warning out to people. So how do we get the warning out to people? There are several ways. The MyShake app is one of the ways. It's now delivered to all Android phones. It goes out to the public alert system called IPAWS in the US, and then it goes to technical users like the BART system. And so, but one of the reason that we sort of been very involved in this process at Berkeley is we wanted to make sure we understand the whole system. If we want to make sure the system works well, you need to understand it all the way from the source to the delivery to the users. That's what we've come to understand through the course of this process. And so at Berkeley, we've been involved in all of these pieces. Obviously, we run a network in Northern California, this EPIC algorithm, as I mentioned, and then we deliver through MyShake. So we're able to see the end-to-end system, and we're able to improve the system as a result of doing that. Okay, so how are we doing? The big question. This is great. You've made all these promises. How we're actually doing in terms of delivering the alerts to people. So we've now had 4 1/3 years. I updated this last week just for you guys. We had 4 1/3 years of public delivery of earthquake early warning. And so how have we been doing? So over that period, we've had 115 correct alerts, true alerts, as in earthquakes that are greater than the magnitude 4.5 cutoff that we've detected and we've sent out an alert. So we've had 115 successes. We've had 3 false events, okay? The 3 false events are the red dots you can see on this map. You can see 2 of them are offshore, so obviously outside the network. We only have stations onshore, of course. And then this is actually a very poor location for an earthquake that was on the California-Nevada border and was poorly located, hence it's in the middle of California. The point is that all 3 false alerts were actually events that are at the edge of the network where we had little coverage. They were also all at the beginning of the system. This hasn't changed for several years now in the fact we've only had 3 false alerts. And then we've had 8 missed alerts. These are earthquakes where the actual magnitude was greater than 4.5, but the system didn't detect them, didn't issue an alert for them. Again, they're all around the edge of the network, as you can see. So the bottom line is, I'd say this is fantastic. I think this is a great success, right? 115 correct alerts compared to 3 false alerts and 8 missed events that were all small events. So to me, this already, we've shown that the system works very well. Okay, so how do you get the alerts if you're in California, Oregon, and Washington? Well, one of the ways you get the alerts is using the MyShake app. Okay, and so you download the MyShake app. You guys can download it as well. It's available for free. You won't get alerts on the MyShake app here, but you will contribute to the global seismic network that I'll talk about in a few moments. So the way you get the alerts is you download the app. But what we've also built into this is we talk to users about what is it that you need. Okay, so of course, the first thing that people want is a warning. That's not surprising. But what happens if we have an earthquake right now? Well, we would get a warning. You would get down on the floor so the lights don't fall off on top of you. But then what would happen? You'd need to know what exactly just happened. Where's the damage? So it also shows a map of where damage occurred based on what people actually report, and then various other pieces of safety information and things like that. So that's what MyShake provides to you. So when does MyShake alert? So there are 2 criteria. First of all, the magnitude has to be greater than 4.5. The estimated magnitude has to be greater than 4.5, which is not a big earthquake. I mean, this 4.5 is a light shake. And then we issue the warning to the area where we estimate the shaking intensity is going to be greater than 3. Okay, so that's pretty low on the intensity scale as well. So the idea is that we send out a warning at this relatively low threshold, because that way people get reminded that we have a warning system. They get the alert, and I'll show you what people think of the alert in a minute. It's a reminder that they live in earthquake country, there are going to be earthquakes, and they will get a warning, and they can think about what they're going to do. But the other thing that's really important is that the goal here is to alert most people who will feel shaking, but it's never going to be perfect. Right? It's not like the ground shaking occurs in this perfect circular region around the epicenter. And so there's these fuzzy edges to the system that will always be the case. Another way of putting that is it doesn't matter what we do, somebody's going to be really upset. Okay, somebody's either going to have not felt shaking, but did get the warning and be upset about it, or somebody is going to feel shaking and not get a warning. Did I do the same thing twice? You understand what I'm saying? So whatever we do, somebody will be upset. And that's something that we've had to adjust to and get used to. But overall, as you'll see, the response is pretty positive. So let me show you 2 examples. I'm going to show you 2 earthquakes of how the system actually performed. This is my favorite example. It's a magnitude 5.1 in the Bay Area. It's my favorite example because I was giving an exam at the time of this earthquake. I teach a large class on earthquakes, and lo and behold, I'm giving the exam in my earthquakes class when this earthquake occurred. Okay, it's a large class, so the exam was actually all done online. And so all of the students are online. I'm on Zoom, so people can come and ask questions if they're having problems. We have this earthquake. Everybody across the Bay Area feels this earthquake. And all of a sudden, all of the students are jumping on this helpline to ask if the exam's going to be cancelled. I said, absolutely not. Can I have more time? Absolutely not. You wouldn't believe how many people thought the exam should be cancelled because we had this earthquake. Anyway, so this is the magnitude 5.1 earthquake. It occurred just to the east of San Jose, where the star is right here. What's shown here, just to explain this time, this is a shake map. The orange scale is the shaking intensity, okay? And so this sort of lighter color is shaking intensity 2, and then this orangish color, the second shade that's shown here, is shaking intensity 3. So our goal, remember, is the shaking intensity 3 region, okay? So that's this darker orange region here. So these folks, this is what I mean by these folks, they're in shaking intensity 2, so you could argue that this is an over alert. But of course it's not. Most people in that region actually felt the shaking, and so it's not a problem. And then these circles are showing the amount of warning time. So the black circle, first of all, this is what we call the blind zone. So it does take time. We actually have to collect data. We have to process the data. We have to get the warning out. So this is the zone where there is no warning. And so this is, one of the catches is that there will likely be a blind zone around the epicenter for all earthquakes, which means the people who are probably going to feel the strongest shaking are not going to get a warning. That's just a reality. We can't get around that. We can't beat the physics. 5 seconds warning out to here, 10 seconds, 15 seconds. The reason these circles are not at sort of equidistant is that this is the actual observed warning time. And so when we built MyShake, when we started, nobody believed you could actually deliver warnings to smartphones fast enough by sending these kind of point-to-point messages fast enough. So we built the system to actually collect receipts and send information back to us about when phones received the warning. And so this is what the data looks like. It's obviously much more complicated than this simplified version, but this is distance along the horizontal axis. And then this is the time of the S wave arrival after the alert. So it's basically the warning time. How much warning did you get before the shaking, the strongest shaking started? And you can see all of these vertical lines is because different phones get the alert at different times. But you can see that there's up to about a bit more than 15 seconds of warning out at the greatest distances. And then, of course, it comes down to 0. This would be the beginning of this blind zone, the dashed line here. So this is the amount of warning for a moderate-sized earthquake in the Bay Area. So we're talking about seconds, tens of seconds, like I said before. This actually... the reason we knew this was a success is this is the newspaper the next day. I was going to say that this was a turning point for earthquake early warning and for the MyShake app. So as I mentioned, it was during the day. It was about 11 o'clock in the morning. I think it was a Friday, maybe it was a Thursday. It was a work day. And I now know this is the perfect earthquake when it comes to earthquake education, right? It's a magnitude 5, so basically no damage is done. Everybody across the Bay Area felt it. It was sort of middle of the morning on a work day. So all of the news outlets were just talking about this earthquake and about the earthquake early warning for the rest of the day. I was driving home at the end of the day with a music station playing on the radio, and lo and behold, the DJ on the station breaks in and says, "Oh, I learned all about earthquake early warning today. You should download the MyShake app." So the point is that the conversation changed with this earthquake, and it was a discussion about early warning, what people needed to do to get the warning. And then this was the headline, but this is the bit I love: miraculous technology. People are amazed by this stuff. Which is great. I'll show you some more examples in a minute, but people get excited about it. And so that's the other broader impact here is people see the technology, they get excited about the technology, and then they start thinking about earthquakes, earthquake preparedness, and broader issues of public safety related to earthquakes. So here's another example. This is another magnitude 5 earthquake in Southern California now. Again, this had warnings, actually more warning time than that, than the last earthquake, up to just a little bit less than a minute's worth of warning time in this particular earthquake. An alert over a large area, like you can see. And this one I included, I collected some of the quotes of feedback that people gave after this one. Okay, this is my favorite, okay? I felt like a prophet. We're making people feel like prophets because they get the warning and before they see the shaking. I downloaded this app after the last earthquake in my area 20 minutes ago. I got the graphics, earthquake warning, drop cover, hold on. Had time, love this, had time to read it, hesitate thinking, do these actually work? I don't think these actually work, do they? then get out of bed and yell across the house to my kids before the chandelier started to swing from the quake. The epicenter was some distance away. This person was away, getting everyone in my family on this app, and I will not hesitate next time. Okay, so a satisfied user. Slow but happy to have it. This person actually got the alert after the shaking, but they were still pleased to get the alert. And this is something that social science has shown us, is that people need two prompts to take action. So if you feel shaking, everybody just kind of looks at each other. Did you feel that? I think I felt that. I'm not sure if I felt that. But if you then get an alert, that's a second. So now you have 2 prompts and you're much more likely to actually take action. They also say, I wish it was on the Apple Watch. It is on an Apple Watch. So they obviously, I don't know why they say that. I'm not going to go through these. There's, people are excited about it. People are excited, and that's great. People are thinking about earthquakes. That's a success in its own right, because people are excited about this. I don't want to pretend there aren't people who are disappointed. Here's an example, somebody who didn't get the alert. This has been a challenge. What we've learned with smartphones is that there is no 100%. There's no way you can guarantee that everybody's going to get it. We've had crazy situations where people have been very upset that their MyShake app didn't deliver the alert, and we work with them and discover that they never downloaded the MyShake app, just to give you one example. But there are also cases where people have downloaded the app and for some reason they're not getting the alert. So I don't want to pretend that this is 100% accurate, successful alert delivery. It's not. It has its limitations. Okay. So this demonstrates that I think that it works well in moderate-sized earthquakes in California. Fortunately, unfortunately, depending on your perspective, we haven't had a test with a big earthquake in California. And so we need to think about that very seriously because, of course, the whole point of having this system is for those really big earthquakes. And then, of course, in Turkey, they have had very large magnitude earthquakes. Just last year, the magnitude 7.8 earthquake had a devastating effect across eastern Turkey. And so what we've done is we've used the data from that to really evaluate what we expect in a large magnitude earthquake in California. And we can do that because, first of all, they have a seismic network, a fantastic seismic network that recorded this earthquake. So the data is available to us. The tectonic situation is also very similar. This is a large strike-slip fault, just like the faults in California are large strike-slip faults. So what we did is we took their seismic data from their network. We fed it in to the EPIC algorithm, making no changes. So this is a blind test in the sense that we just take the data, we feed it into the algorithm as it exists. And sure enough, it detects the earthquake. That's not surprising. These are the magnitude estimates, right? This was a magnitude 7.8. So this underestimates the magnitude of the earthquake. Now, that's actually not a surprise. As I mentioned at the beginning, EPIC is a point source algorithm. It's focused on recognizing the earthquake immediately, but its limitation is it doesn't recognize the full extent of the magnitude. So this estimated it to be a magnitude 6.1 initially, 5 seconds after the earthquake initiated, and it got up to a magnitude 6.4. Okay, the Finder algorithm does better than that, but I'm just going to show you, even with this, what does the performance look like? Because, of course, we also know how the MyShake delivery system works. We have models that show the latency of the delivery system depending on the number of users. So we can run a complete end-to-end scenario for this earthquake without any tinkering with the algorithm to see how this would perform. Okay, so that's what we did. And this is what you get in terms of the warning time map. Okay, so again, the same shake map in this orange scale. So these dark red regions, of course, are the regions with the strongest shaking. This is the section of the fault that actually ruptured, the strike-slip fault that ruptured in this particular earthquake. This blind zone, the no warning zone, sorry, it's difficult to see just because this is such a large area, but is this black circle in the middle here. It's about 25 kilometers radius from the epicenter of the earthquake. And this is a region where the shaking intensity 8. It's a very strong shaking, obviously a lot of damage done very close to the epicenter. There would be no warning for that region. But then once you get to Antakya, which if you may remember is where there was a very large amount of damage, collapsed buildings, in Antakya, there's 20 seconds of warning, and that's before the first S-wave arrival, right? So that's before that red circle in the animation I showed you for California. It's actually more than a minute until the strongest shaking, just because of the size of the earthquake. So that's the amount of warning that they have. And then the largest amount of warning comes out to this distance here. It's over 100 seconds worth of warning. And that's even with the underestimate of the magnitude. So this we found incredibly encouraging, to be honest. The fact that we got this performance with just using the algorithms exactly as they were. Of course, we can use this and go and use this as an illustration of what to expect in California. As I mentioned, California's strike-slip faults. And so what we've done here is we've literally taken the fault from Turkey and rotated it so that this is the San Andreas fault running down here and the Hayward fault running up through the East Bay. So we chose this particular orientation for the fault. This is actually very similar to the Loma Prieta earthquake location epicenter. And then this is the same seismic stations that we had from Turkey just translated. And this is to compare it to the actual seismic network that we have in California. The point being here that we would actually expect to do a little bit better if this earthquake happened in California, just because we have so many more earthquakes. But again, we can use this to translate to the warning times. And so it's the same story. There's no warning close to the epicenter, right? So that would be Santa Cruz in this particular example. But in the South Bay here, where we have shaking intensity 8 to 9, there's 10 to 20 seconds worth of warning and 20 to 30 seconds of warning in the North Bay. So the point being here that this gives us confidence that we can have more significant warning times, even in these largest magnitude earthquakes, based on this test of using the data from Turkey. Okay, so before I leave the early warning part here, I just wanted to kind of come back to Canada. This is again from my colleagues at Natural Resources Canada. This is just to illustrate, obviously it's the same system, it's the same setup. And so this is an example of this earthquake that happened relatively recently, magnitude 6 earthquake in 1988, and the amount of warning time that they would expect from their system. This is perhaps the slide that is most interesting to take away. This is the slide that shows the alert regions that they're going to have. This is obviously in the west, and then over here in the east. It doesn't quite reach us here in Toronto, the alert region, the active region. But this is showing the annual chance of an earthquake early warning alert, right? So you can see, for example, down in this region, I'm not going to the hotspot here. In the hotspot, there's a 5% chance. Down here, we're down at like a 3% chance of an early warning alert in a given year. That's pretty low. I mean, there's obviously very low seismicity. So it's kind of amazing to see that this is motivating, early warning is motivating the creation of this network on this very large scale. Okay, so how good is earthquake early warning? I mean, we've been pretty happy, I've got to be honest, with the performance of the system up until this point. I'd say the event detection accuracy is good. I showed you the ratio of true alerts to false alerts to missed alerts. People are pleased and excited. We've had very little complaints about earthquake early warning. We've had very few complaints. The ratio of people who are excited to those who complain about the system is very positive. And as I've shown you, we're going to get seconds to tens of seconds of warning of strong shaking in some of the largest events. I haven't included this just because of time, but I do want to sort of acknowledge that I think one of the areas we have to do a better job is how people respond to these alerts. So right now, the surveys show that what people do when they get the alert is they mentally prepare, as in like they get the warning and they start thinking about what's about to happen. And of course, what we want to happen is we want them to get the warning and then we want them to get under a sturdy table. And so that's something that still needs a little more work in terms of training people, educating people about what they need to do. Okay, so that's earthquake early warning and how we're doing. So let's move on and talk about smartphone seismology and what we can do with smartphone seismology. So right now, MikeShake is completely dominated on the West Coast by the idea of delivering alerts, because that's what everybody sees, that's what everybody talks about. But that's not why we built MikeShake. We built MikeShake to detect earthquakes. Right? So seismology is a data-limited science. We don't have as much data as we would like to constrain earthquake processes. And so that's why we started experimenting with an app, is the idea we want to use the accelerometer in your phone to detect the next earthquake. Okay, that was the goal behind MikeShake. And so when we launched MikeShake originally in 2016, it was about earthquake detection. The earthquake alert delivery came much later in 2019. And so this is an earthquake, a magnitude 5.2 earthquake, Borrego Springs in Southern California. The earthquake's right about here, you'll see in a moment. All of these dots, these are MyShake phones, people who had downloaded MyShake app on this particular date, and their phone was in monitoring mode. So their phone was stationary, it was plugged into power, and it was monitoring, waiting for an earthquake when this particular earthquake happens. That's why there are dots on this map. I'm going to run an animation that shows how these phones triggered in the earthquake. When they trigger, they turn orange. So this orange dot up here is that there's this one phone that just happened to randomly trigger half a second before this particular frame that I'm showing. So let's run the animation. So this is the epicenter of the earthquake. This is the P wave of the earthquake, the S wave of the earthquake. So as the P wave passes through Palm Springs, you can see the MyShake phones all triggering in this earthquake. And as the P wave and then the S wave get further, you can see these are triggering on the P wave. And then additional phones will actually trigger on the S wave. But the ratio, the number of phones that are triggering as this P wave and S wave get further out reduces, right? So the amplitude is of the P wave or the S wave is reducing, fewer phones trigger. But remember, this is individual private people's phones who happen to have downloaded the app. Their phone happens to be sat still and is in monitoring mode at the time of this earthquake. So this shows the power of using smartphones to detect earthquakes. Given how many phones are out there relative to the number of people who would download MyShake at this point. So that was the idea behind MyShake originally, was to collect data, to collect seismic waveform data. And so it was set up to trigger, to go into this monitoring mode, to trigger and collect the waveform data whenever it sees earthquake shaking and put that in a database that we can use for research, to look at shaking on a very detailed basis, and to look at the response of buildings. So that was the idea behind MyShake. I have to show a waveform, otherwise seismologists just don't believe me that this is possible, okay? So this is a waveform from just 3.4 kilometers from the epicenter of this magnitude 4.5 earthquake. Clearly shows the P wave arrival, shows the S wave arrival on this waveform. So that's what MyShake can do. What smartphones can do is that we have data much closer to the epicenter than if we just had the traditional seismic network. Of course, by building the early warning system, unfortunately, we were also damaging some of our data. So here's another example. This is the same earthquake for which we issued an alert. And this phone, this is the vibration pulse of the alert reaching the phone, basically at about the same time that the P wave arrived at the phone. So we've actually gone and destroyed our own waveform by issuing an alert. So there's a bit of a unfortunate feedback, not that we're going to stop issuing the alerts, but that's one of the realities. The point is that we can do this. So we showed that phones can detect earthquakes. We showed that we can get high quality data. We did it on a reasonable scale. And so this is the point at which, as my 13-year-old would say, well, you need to go talk to Google, because Google does everything. So, hey, Google, you should do earthquake early warning. So we went and we kind of pitched this case to them that they should think about actually doing this. I did this with my graduate student at the time, Chin Kai Kong, who was the graduate student who basically developed the MyShake app. And lo and behold, we were successful in getting their attention, getting Android to integrate. They basically took the MyShake technology, embedded it in the Android operating system. And that means that all of a sudden, literally overnight, every Android phone becomes a seismometer that's detecting earthquakes. So this is, in fact, that very same magnitude 4.5 earthquake I just showed you MyShake waveforms from. But this is now, all of these green zones are regions where there are Android phones in monitoring mode for this particular earthquake. I'm going to show you what the Android network looks like when this particular earthquake happened. I don't remember off the top of my head how many phones actually triggered for this particular earthquake, but you can see it's a very large number of devices that triggered. So this was a great success. This evolved from a detection capability into a detection and alerting capability. And so that is the Android earthquake early warning system that we actually have today. The Android system is now delivering alerts in 97 countries around the world. And just to show the scale of this shows the number of people who had access to earthquake early warning over the years. This is the first public warning system in Mexico City. Japan came online in 2007. The orange is actually the Shake Alert system in California. And then this is when the Android system started to deliver alerts, and they scaled up. 2.5 billion people have access to earthquake early warning right now as a result of the Android early warning system. So it's been great to see that progress being made. Okay, So that's the smartphone, kind of quick overview to the smartphone piece. And what I want to do now is just squeeze in a couple, well, I don't think I have time for two. I'm going to show you one example of what I think comes next. Right, so we built the early warning system, we made the case, but we really want to now go and use that data to go beyond what we're currently able to do. And I had two examples. One is actually improving earthquake ground motion prediction. I'm going to skip over that. I'm going to go straight to the building damage detection because it connects directly to the hazard piece. Can we use this additional data to estimate building damage? So you're going to get a very quick flyby of the ground motion piece, which I'm going to skip over. And we're going to talk about, as you can see, I clearly had too many slides. We're going to talk about predicting ground motion in buildings, right? So one of the reasons that we want to accurately predict ground motion, most importantly, is we need to know how to build those buildings that are not going to collapse in earthquakes. So by predicting future ground motions, we can build buildings that we don't expect to collapse. That's one of the most important pieces is the building design. But also, we need to then actually evaluate and demonstrate that buildings are built to the standards that we expect, right? So are we sure that the buildings we've built are not going to be damaged in earthquakes and are safe to occupy after we've had an earthquake? And that's the area of structural health monitoring. So understanding the structural health of a building before earthquakes and then after major damaging earthquakes. And so this is one of the things that we think we can do with MyShake, and the value of this is it's often difficult to put a seismometer in buildings because the building owner doesn't want you to do that, right, for obvious reasons. But if you can do this with smartphones, you can actually evaluate the safety of a building after an earthquake without having to ask anybody's permission. Because if you live or work in the building, you take the phone in and it's going to provide information about structural health. Okay, so how does this work? Well, buildings, they vibrate just like a bell. I don't have to explain that to this group, but buildings, they vibrate just like a bell, which means that they have these modes of vibration that are a function of the structure's mass, its stiffness, and its damping, okay? And so the way you can hit this bell, cause the building to vibrate, is of course with earthquake shaking. So when an earthquake occurs, you can measure how the building vibrates to tell you about the structural health of the building. But also, you can do this with wind. Wind is also a significant force, particularly on high-rise buildings, and causes these buildings to vibrate. So if there's damage to a building structure, it causes these modal frequencies to change, right? So if we can measure the modal frequencies, we know what the structural health of a building is. And so that's what we want to do with MyShake. So we started by doing this on a shake table test. This is work of a graduate student, Serena Patel, on a shake table at Berkeley. Is it going to work? It's not a huge amount of shaking that they do in this particular case, but this is an example of the Izmit earthquake in Turkey in 1999, where they shake the building, and we have phones throughout this three-story building, so we can record the ground shaking, and that's what we're seeing here. But we can use this to actually observe the damage to the building, right? So to illustrate that, this is the recording from one of the phones that's in this building for this particular earthquake. And the way that you do this is even just within the earthquake time period itself, you can see what the pre-earthquake fundamental mode is, 3.25 hertz in this particular case. You can then see what happens during the earthquake. There we go. During the earthquake, the modal frequency drops. So it actually becomes more flexible, okay, during the earthquake. And then you expect the building to go back to the same state after the earthquake. But in fact, it doesn't. It comes back to 3.17 hertz, okay? And so this is an illustration. This change is actual damage. It's a demonstration that the building structure was damaged. And what actually happened in this case is that these struts, not the big yellow ones, but these silver ones are what they were testing, and they were partially damaged. And that's why you have this change in the frequency. So this is how you can see damage in a building using the recordings. But you don't have to just use earthquakes. You can also use the wind to tell this, right? So traditional seismometers can measure the ambient vibrations of buildings just due to the wind blowing on the side of them. And so this is a traditional seismic station or traditional sensor in a 60-story high-rise in San Francisco. This is an hour of data. you just take the frequency spectrum of this data and you see the modal frequencies of this building. These are the two fundamental modes in the two horizontal directions. And then this is a higher mode, this mode here. This is a higher mode that you just see one frequency for in this particular building. Okay, so we have this building, we have a traditional sensor in there so we can see what the modal frequencies are. Can we do the same with phones? And so we've actually been collecting this data this winter. We've had these big storms. It's when you have big storms, the wind causes the buildings to really oscillate. And so you can do a much better job. This is the seismometer in this building. It's just a phone that's plugged in somebody's closet. Here's 5 minutes of data. The signal is so strong here, you can actually just see it in the time series. So we only have 5-minute segments of data, but we can still use this to extract the frequency of this building. So we can extract the modal frequency of this building. Here's another example. For this particular case, we're exciting both the fundamental mode and the overtone. Another example of the fundamental mode, you get the idea. So every time the phone triggers, it collects these 5 minutes of data, and we can see what's going on. This is the Y component, so the other horizontal component, slightly different frequency, 0.26, matching exactly what we were seeing with this traditional sensor. So the point is that this demonstrates we can use these phones that are just private people's phones that have been put in the corner of their apartment, left overnight, to map the structural characteristics across the city. And so the concept we have here, so it's a concept, we haven't done this yet. The concept that we have here is that in peacetime, so right now, we can gradually work our way with all of these phones, these MyShake phones that are out across the city. We can go and we can measure the modal frequencies of these buildings. Okay, so we have a database which shows what the modal frequencies of these buildings are. Then, once you have an earthquake, we can ask the question, well, which buildings have structural damage? Of course, if those buildings have been seriously damaged, it's very obvious, you can see. But the concern is things like after the Northridge earthquake, where they had damaged welds within the building. They couldn't see that. The structural engineers couldn't see it by inspection, but it changes the frequency content of the building. So we would then be able to see what these modal frequencies are after an earthquake and identify which buildings are a cause of concern. And of course, you could do this globally. Right? You could do this in every city around the world. And that's the concept. Okay, so let me wrap up. I've used up more of your time than I expected. So key takeaways here. So earthquake early warning, first of all, I think we've successfully implemented. I mean, I think we can say this is working. It's out there. It's delivering alerts. I think we have sufficient accuracy of event detection. It's never going to be perfectly accurate, but I think the accuracy is good enough that people are satisfied and they trust the alerts that they're receiving. Seconds to tens of seconds of warning is what people are getting, and there's no question, there's a very enthusiastic response right now. We'll see a few years from now, it's possible that it's new technology, people are excited, but right now, people are very enthusiastic, and of course, as I've said, it's coming to Canada. Okay, and this also then led to smartphone seismology, right? Again, this application led to the expansion networks and smartphone seismology. Currently, it's operating on 2 billion devices around the globe. The Android system is actually delivering alerts in 97 countries. That will probably tick up over the coming years as additional countries are added. And then in the case of MyShake, we're really trying to think now about how we can use smartphone instruments to actually kind of do the next generation of understanding hazards and reducing hazards. I didn't talk about it, but in terms of improved ground motion models for future shaking, and then in this example I did show of structural health monitoring. All right, I'm going to stop there. Thank you very much for your attention. I very much appreciate the fact you're all here, and I'm happy to answer your questions.